Hello and welcome again to this course on the fundamentals of attosecond science and technology being offered from IIT Madras and IIT Tirupati by us. It's indeed our pleasure to introduce this subject to you through this course. Three of us will be handling this course, myself Sivarama Krishnan from IIT Madras, Professor Deshmukh and Professor Vinay Pramod from IIT Tirupati. In this course, we will take you all the way from really the fundamentals of not only attosecond science and technology, but also of some allied areas which serve as a primer to this course, all the way to the current advancements in this field, particularly in the context of the fact that this year 2023, the Nobel Prize in Physics was awarded to three pioneers in this field, Professor Anne Lully, Professor P. Agostini and Professor Ferenc Krauss for their contributions to the genesis of attosecond science and technology. One of the important aspects of attosecond science and technology is the fact that it is primarily based on optics and electromagnetics as well as the physics of quantum systems and objects. Therefore, it is only appropriate that in this course, which is intended for a relatively wide audience, we begin with a primer on optics and electromagnetics. So, that is what we are going to take up in this lecture in the first module of this course, which is dedicated to the primers that are involved in attosecond science and technology. Before I proceed any further, I would like to share some references with the student audience to this course. The information that I am providing today is based on these sources and possibly others that we have come across. There are three books. It is not intended that we are asking you to own any of these books. It is just to present to you the context and original source, some of the important original sources of information. And I am also very grateful to Professor Rick Trebino, a pioneer in femtosecond science and technology, who created an excellent repository of lecture materials and inputs for pedagogy in this area. This lecture's outline is as follows, and we have crafted it so that anybody with a background in science or engineering can begin walking with us right from the beginning with very little presumption of any form of prerequisites. It's possible that someone in the audience with a degree or ongoing degree or completed degree in physics or electrical engineering or photonics or something of this nature would have certain advantages in taking up this course. All the same, for a more general learner in this course, we are intending to ramp you up right from ground zero, if you wish, things that you very likely know, all the way from undergraduate or possibly even high school education, so that you can quickly catch up with the prerequisites and the primer for this course, which will aid in understanding the rest of what is going to follow. So, we will begin where we need to begin things, that is with waves and in general, and particularly look at one dimensional waves and the equation, which are fairly straightforward to handle and help us to build some intuition, and then look at the topic of interest for this course in more particular terms, which is one dimensional light waves, the solutions for the one dimensional wave equation of light waves, and the property of waves in general, but particularly in the context of light waves, which include wavelength, time period, frequency, phase velocity and more. So, let us ask and answer the following question, that is, what is a wave as such? What do we mean by waves? We look at waves all around us in some sense, like in art, but in real life too, especially if you're in a seaside city like Chennai, but possibly also in a lake or a pond, or maybe even in a tub of water anywhere, right? So, but there could also be other forms of waves. We experience sound waves, we experience light waves, which trigger our sensory organs. It so happens, as you may already know, that there is a general formalism, a mathematical formalism for treating all waves in general, and that formalism happens to be the so-called wave equation, which is a differential equation. So, we will take the notion of a wave, which we essentially learn in various aspects of science and technology courses earlier, and develop this and put it on a firm mathematical footing using specific functional forms which are indicated over here. And we will also then develop a differential equation which we can apply to many different contexts, especially in the one dimensional case. We can also take this forward to 2 and multiple dimensions, explore harmonic waves and their characteristics, wavelength, frequency, period and so on, and dwell upon some of the more advanced concepts. So, what is a wave? We may well argue that anything that moves has the nature of a wave. So, propagation or motion is a very important feature of a wave. As against material objects, the complement to a wave is a particle. A particle has mass, it has inertia, and it is governed by laws of classical and even quantum physics, depending upon the scale and the size. But now a wave is a propagating phenomenon. So, that is a very important aspect of the physics and technology of waves. So, something that moves essentially also is said to propagate, right. So, a wave has a shape, the amplitude of a wave has a shape. At any instant of time, we can choose with the instant of time from which we start observing a wave, or we take interest in a wave that is present in a medium in general, or it could be a light wave which does not necessarily need a medium to be present or even propagating. So, whatever the case may be, let us consider this to be having a certain functional form for the one dimensional case, and let us call that function f of x. F and x are our two favorite symbols in mathematics for a function and x for a variable. So, the next thing that we have to set ourselves up to is the task of making the change that happens in the spatial coordinate x, so that the wave can in essence propagate in some direction. So, let us say that the wave we are interested in propagates in the so called positive x direction, which is from left to right on this screen. This is the direction in which the variable x increases. So, the wave was centered at x is equal to 0, and after some passage of time it is moved, and it is next we concern ourselves with the instant of time where the wave is now centered at x is equal to 1, right. So, the mathematical description of this wave is hinged upon this one very important feature, that given some idealization, that the shape of the wave, which here looks like a spike or a pulse, or you can even say some kind of inverted bell shape, retains its form as it makes a move from being centered at x is equal to 0 to x is equal to 1, right. Therefore, the feature that we should concern ourselves with in describing this wave is the fact that the shape of the wave should not have changed as it made its propagation from being centered at x is equal to 0 to x is equal to 1, right. The variable for the function f which describes this shape should be the same, and everything else should have shifted from being centered at x is equal to 0 to x is equal to 1, or as time passes, the wave can move further forward from x is equal to 1 to being centered at x is equal to 2, but retaining the same functional form, and as time passes it also goes from x is equal to 2 to x is equal to 3. In all these instances, the shape of the wave is retained and is characterized by the same function f. If you are familiar with it, we could describe this as a Gaussian shape or a Lorentzian shape or something of that nature to describe to become more particular about what the function f should turn out to be. So, let us just make a note about this. F could be something like a Gaussian, it could be a Lorentzian function, or it could be even a hyperbolic secant function, as the case may be, since all these functions are equally good to describe this form of a pulse or a series of pulses, right. So, now the larger point here is the fact that the wave has essentially moved with a velocity v in the positive x direction, that is in the increasing direction of x, and the motion of this wave going from a center x is equal to 0 to 1 to 3 to 4 is described by a function which now has a form f, the function of x minus vt. The argument to this function must have the form x, which is the spatial coordinate, minus v, which is the velocity. In this case, the velocity is restricted to positive values, so that we can keep this unambiguous, and t, the variable that denotes time. So, f of x minus vt represents a wave that moves rightward on your screen, or the positive x direction propagating forward. Likewise, we could have figured out a scenario in which this wave could have moved essentially in the negative x direction, in which case the functional form that describes this wave motion would have had the form x, f of x plus vt, where v is essentially again positive valued. V is the velocity of this wave. So, that is a functional description of the wave using the concept that a wave is something that moves, and in this case we have limited ourselves to one dimension. Let us proceed further and develop a differential equation which can describe wave phenomena. This is again something you may have come across in some earlier courses. So, this may be a refresher for you. Now, considering the fact that a propagating wave is well described by a function of time and space in one dimension, that is x and t, by a function f of xt of the form f of x minus vt or plus vt, corresponding to a wave propagating in the positive or the negative direction of the spatial coordinate x, we can write down a differential equation which captures this phenomenon in a very local sense in the following way. This linear second order differential equation d2f by dx2, the second derivative of x with respect to the spatial coordinate alone, so it is the partial derivative, minus 1 divided by the square of the velocity v of the wave, which remember we made it positive definite in the previous definition of the of the function that describes the wave, which is f of x comma t. Now 1 minus v square is multiplied by d2f by dt2. This left hand side in this wave equation is equated to 0. This is the simplest and a very ideal form of a propagating wave in one dimension described by a differential equation. Note that when we write down a differential equation like this, from its very nature, this is a very local description of the wave at a spatial point x and at a given time t. Now this equation, irrespective of what the specific form of f is, admits all solutions which have this simple functional form of f being a function of x and t. That is, x and t in this solution should combine in this linear form of x plus or minus vt. And of course, since this is a phenomenon described by a second order differential equation, those functions which are twice differentiable can be used to describe propagating waves in one dimension in this case, or particularly in more spatial dimensions as the case may be elsewhere. Now let us just convince ourselves that this functional form, that is f of x plus or minus vt, indeed solves this differential equation which we call the wave equation in this one dimensional case, right. So let us take the functional form f of x plus or minus vt and compress the information in this x plus minus vt into a substitution where u is x plus or minus vt, so that this function f of x plus or minus vt becomes essentially f of u, and we need the derivatives in order to do the math. So let us take the partial derivative of u with respect to x alone. The partial derivative of u with respect to x alone is just unity, and the partial derivative of u with respect to t alone is a plus or minus v, where v is the velocity. In this case, v is also a constant apart from being a positive valued parameter, right. So we can then use the chain rule of calculus in order to proceed further and compute the partial derivative of f with respect to x using the intermediate substitution for u. So df by dx is df by du multiplying du by dx, product of two derivatives, and then likewise for the temporal part, df by dt is essentially equal to df by du multiplying du by dt. In this case, this turns out to be that df by dt is a plus or minus v multiplying df by du. But what we need are second derivatives, because the wave equation contains two second partial derivatives of f, one partial derivative with respect to x and the other with respect to t. So let us now compute these two second order partial derivatives. d2f by dx2 is essentially d2f by du2 as we have shown in the previous step for the first derivative, and d2f by dt2 is v square times d2f by du2. Okay. So note that we have done a very clever thing. Both the second derivative with respect to x and with respect to t are now written in terms of the same parameter u, and we have used v, which is a constant in this problem. So now we are ready to more or less prove the fact that these solutions of the form f of x minus vt or plus vt, as the case may be, indeed solve the one dimensional wave equation identically by simple substitution, right. So substitute these two into the wave equation, which read as follows. The wave equation read d2f by dx2 minus 1 over v square d2f by dt square is equal to a 0. Now, substitute for d2f by dx2, which is from this earlier result, and substitute for d2f by dt2 from this earlier result, plug these two into this equation, and these will give us the form in the intermediate step here. So, we have here d2f by du2 first coming from the second partial derivative with respect to x, and then we have v square multiplying d2f by du2 arising out of the substitution for d2f by dt2, the second partial derivative with respect to t. We already have in this equation a coefficient which is minus 1 over v square. So, therefore, the two v squares cancel themselves out, and the two terms in the intermediate equation are therefore d2f by dt2 minus d2f by dt2, which is identically 0. So, therefore, it is a simple piece of math which essentially has shown us that all solutions of the form f of x plus or minus vt solve this master equation, the wave equation. Now, I must add a note here to say that this form of the wave equation describes a very idealized scenario where the wave, which is in this case a pulse which we saw, which has something of an inverted bell shape that I have now just tried to sketch on the bottom right of your screen. It presents a very idealized situation where this propagates through a medium and it perfectly retains its shape all throughout its propagation, right. So, this wave is kind of an eternal pulse that is propagating in this case, which is of course an idealization. In real media, there are losses. So, the amplitude of this pulse can diminish as the pulse propagates. Further, there could be other physical realities of media such as dispersion and others, which we will talk about a lot in this course, which would lead to these propagating pulses getting distorted and suffering distortions of kinds like the width of the pulse, the temporal width of the pulse getting stretched, apart from losses and such other effects too taking place. In order to describe more physical and real waves, we can again use appropriate differential equations, which again we will have plenty of occasion to visit in this course. But then, as your intuition may probably already tell you, this idealized form of the wave equation that we have been talking about up to now, which is d2f by dx2 minus 1 over v square d2f by dt2, will no longer be sufficient. We will have to add additional terms to take care of further physical phenomena. But then it is always good to start with and build up heuristics with the idealized one-dimensional wave equation. So, a typical wave need not necessarily be just a finite pulse. Now, a typical wave can look like what we have shown here. It keeps propagating on and on in a sort of continuous form like a stream. It could be a stream of water waves, it could be a stream of light waves, or it could be a stream of sound waves, as the case may be.